Yes, we can start. So welcome to everybody. I'm Ilić Strambini and I'm chairing this section. The speaker is Stefan Ilić, and he will present his last research result with more or less 35 minutes talk. And after that, there will be 50 minutes for questions. But if you have any questions during the talk, please raise your hand or just write a message in the chat, and we can stop the talk anytime and reply to your question. So I had the opportunity to work with Stefan Ilić in the last year. He's a very young but promising scientist in solid state with interest in spin system, superconductivity, and correlated system. Recently, we also published a promising work on supercurrent diodes based on tunnel bias, so our supercurrent diodes on quasi-particle. But today is going to show you supercurrent diode effect in Rashba superconductor with arbitrary disorder. So Stefan, it's your turn. Please, you can start.
Thank you, Ilić, for the introduction. So hello, everyone. Thank you for coming to my talk. So as Ilić said, I will present my latest paper on supercurrent diode effect in Rasba superconductors with arbitrary disorder. This is a work that was done in collaboration with Sebastian Bergeret in CMF San Sebastian, and the work was funded by the SuperTED European project. First of all, let me start by introducing the supercurrent diodes, although probably many of you already know. So supercurrent diode is a system where in the one direction supercurrent can flow, while in the other direction only a normal dissipative current can flow. And this kind of element, as you can imagine, can have a vast number of applications in low temperature and superconducting electronics. And a recent experiment that started the surge of interest in this topic recently, this paper by Ando published in 2020, which demonstrated this effect in a complex structure of this type, which is believed to have strong Rashba spin orbit coupling, where the in-plane magnetic field was applied. And then the diode effect, the origin of the diode effect is likely due to a magnetoelectric phenomenon due to combination of Rashba spin orbit and the magnetic field. So here below is the result of the experiment. So if we look, for instance, at the orange curve, we will see that the critical current for one direction and the other are different. So that means that in the region which is in between these two critical currents, our system will behave as a supercurrent diode. So supercurrent in one direction while the ordinary current flows in the other. But this device will work as a diode only in this limited current regime. So the goal of experiments and of theories now is to find conditions to maximize this difference between the two supercurrents, which would make the potential for application of these diodes greater and devices more versatile. So ever since this experiment, there were many other experiments that found similar effects. So for instance, in Josephson junctions, then in so-called Ising superconductors, for instance, few layer niobium diselenide, also in twisted graphene structures, tri-layers, bi-layers, and so on. But I should point out that the non-reciprocity of the critical current was measured as early as 2005 in systems of ferromagnet and a superconductor. And here the diode effect originates from the stray fields of the ferromagnet. Now, the origin of the diode effect can be understood relatively simply in terms of these symmetry arguments. So if both time reversal and inversion symmetry are broken in the system, that means that our current J of Q is not equal to minus J at minus Q, where Q is the phase gradient. So if we plot this, so here is the situation without time reversal symmetry breaking. So let's say without magnetic field, and we see a symmetric curve of the current with respect to the phase gradient. But then when we turn on the symmetry breaking field, then we get this asymmetric picture. And there are two consequences of this inequality. First of all, that the ground state of the system, or the state where the current is equal to 0, is not at 0 phase gradient, but at finite phase gradient. So that means that our superconductivity is spatially modulated by this helical modulation Q0. This is the so-called helical superconducting phase. Moreover, we see that at 0 phase gradient, there is a finite current, which is known as anomalous current. Another consequence of the inequality is that now we can have, unequal minima and maxima of this curve, which corresponds to critical currents. So that means different critical currents for the two directions. But analogous picture also holds in Josephson junctions, where one should replace the supercurrent with the Josephson current and the phase gradient with just the phase. And this inequality then leads to anomalous Josephson effect or a finite effect, which means that even in the absence of the phase difference, a current can flow, the anomalous current, or that the zero of the current is at some finite phase phi naught. And also the diode effect analogously for Josephson junction, which means that the maximum and minima in the current phase relation are not the same. Now, all these effects actually phenomenologically stem from the term in the free energy of the superconductor, which is linear in gradients. So for specific example of Rashba spin orbit coupling, this term looks like this. This is the so-called Lifshitz invariant. So here, if we imagine a 2D Rashba superconductor whose symmetry breaking is along the z direction, so perpendicular to the superconductor, and H is in plane magnetic field, then we see that the supercurrent, that the maximum magnetoelectric or the diode effect can be expected if the current and the field are perpendicular to each other. These kinds of effects will be covered in our upcoming review article, which we are writing in collaboration with the group of Francesco Giasotto. Now, specifically for our work, I'm focusing on the diode effect in a 2D superconductor with strong Rashba spin orbit coupling. And this situation was studied previously in these works, but for clean systems only. So in the absence of any impurities. And the way the effect was studied was using the phenomenological Ginzburg-Landau theories or fully numerically. Now, what I want to do here is a bit different. I want to apply quasi-classical theory for superconductors with strong Rashba spin orbit to this problem, which has several advantages. So quasi-classical theory involves solving transport-like equations for superconductors. And it allows for simple and transparent calculations, which can be, for the most part, analytical. And moreover, we can include arbitrary disorder within this theory, which is important because many of these structures, realistic structures, are probably pretty disordered. And this approach allows us to explore the full phase diagram of the Rashba superconductor. So for instance, here is a little preview of our result where you can see that we are able to map the non-reciprocity of the critical current in the full phase diagram. And moreover, we can derive the Ginzburg-Landau theory microscopically from our equations, which allows us to connect full self-consistent numerical calculations and also phenomenological considerations. So here is the outline of my talk. First, I will introduce helical superconductivity and talk a little bit in more detail about this. This is the main ingredient that drives the diode effect in these systems. And then I will present the main tool which we use, which is the quasi-classical theory, which then I will apply first in the clean systems and later in disordered systems. So let us take a Rashba material with very strong Rashba spin-orbit coupling and a chemical potential which is high in the conduction band. And then the material has at the Fermi level has these two Fermi surfaces which are circular, and at zero field they have the same center. And then the pairing of Cooper pairs will then happen within each band. So one helical band and the other, and within each helical band we can have pairing of K and minus K. But then let us now apply a field, and what happens is that the centers of these two Fermi surfaces get displaced, but by an opposite amount. So the larger Fermi surface goes down and the smaller goes up. And by the way, these Fermi surfaces have different densities of states, with the outer one having larger density of states than the inner one. And the ratio of the density of states is determined by the strength of spin-orbit coupling. Now, once the field is applied and the Fermi surfaces are displaced, the pairing can still occur through the center of the respective Fermi surface. But now the pairing will have some finite momentum. So we will have finite momentum pairing or modulated helical superconductivity. But we should note that the two helical bands prefer opposite modulations of the or opposite helical modulations. So what will happen is that there will be some competition between the two bands if field is sufficiently large. Now, if field is low, both bands can contribute to superconductivity, but if field is sufficient, if field is very large, only the outer band with the larger density of states can contribute to superconductivity. Now, there is one complication, is that the helical phase, which I mentioned previously, is not the whole picture. And what can happen, particularly if the difference of the two density of states of the two bands is small, what can happen is that instead of the helical phase, so-called multiple Q or stripe phase can stabilize. So for instance, if we neglect the difference of the density of states of the two bands, so delta n is 0, what we have is that the helical state can exist only in a very small part of the phase diagram, while the rest of the phase, the majority of the phase diagram will be occupied by uniform phase and this multiple Q or stripe phase. But then once we introduce even a very small amount of the difference, then we see that the helical phase actually occupies the majority of the phase diagram, and then the stripe phase exists at low temperatures and some moderate fields. And then further increasing spin-orbit coupling increases delta n, which finally then leads to shrinking of this region of the stripe phase. And finally, the stripe phase cannot exist anymore for delta n when it reaches 0.25. Now, in the rest of my talk, I will neglect this stripe phase for simplicity. So it remains an interesting question of how it will affect the diode effect. So this is justified because the majority of the phase diagram is in the helical phase. And moreover, once you add disorder, the stripe phase is also quickly suppressed. Now, again, here I plot some phase diagrams of the helical superconductors when spin-orbit coupling is large. And here you can see that as a consequence of spin-orbit coupling, the upper critical field is greatly enhanced. So it goes well beyond the Pauli limit. So this is a well-known feature of non-centrosymmetric superconductors. But maybe more importantly for us is how the helical modulation Q0 behaves. So we see here, for instance, in the red curve that at low fields, the helical modulation is weak, but then it goes through a crossover and it becomes much larger. And this is the consequence of the two helical bands and them competing with opposing helical modulations. So at low fields, both bands can contribute to superconductivity, and the Q0 is determined by the balance of two bands. So this is the situation at low fields. But at high fields, only the band with a higher density of states contributes, while the other band becomes less relevant. And that leads to a crossover between what we call a weak helical phase with a small modulation vector given by this expression, and a strong helical phase with a modulation vector given by this expression. And this crossover, as you will see later, between weak and strong helical phase will be very important later on for the diode effect. Now that we have established the basics of the helical phase, now I will talk a little bit about the main tools for my calculation, that is the quasi-classical theory. So as I said before, when Rashba spin-orbit coupling is very strong, it is convenient to work in the basis of two helical bands. So what means very strong? It means that spin-orbit coupling energy given by this is much larger than the superconducting gap, the Zeeman field, and the inverse scattering time. So all other energy scales except the chemical potential. And moreover, the Fermi velocity V can be larger or proportional to Rashba velocity alpha. Now, the two helical bands shown here are parameterized by the band index, which can be plus or minus 1. The two bands have the same Fermi velocity given by this expression, but different density of states, which depends on the magnitude of spin-orbit coupling. And then the main equation which we use is a transport-like equation for superconductors, the Eilenberger equation shown here. So the main object of this theory is the quasi-classical Green's function G lambda. So knowing G lambda, using it, we can calculate observables such as the currents and so on. So here, N is a unit vector which describes the directions of the Fermi momentum, and this derivative, this covariant derivative, contains the usual gradient, but also the exchange field in this way, in a different way for the two helical bands. Then here omega is the Matsubara frequency and delta is the superconducting self-energy, which is off diagonal in the Nambu space. And then disorder is described by this collision term on the right-hand side. If this condition of strong Rashba spin orbit is fulfilled, that means that actually the only type of pairing we need to consider is intra-band pairing. So pairing within one helical band and pairing within the other band, while interband pairing, so pairing between the two bands can be neglected. And that means that the structure of our Green's function in the space of two bands is diagonal. So it has this structure where G plus and G minus have only structure in the Nambu space. And moreover, there is a normalization condition, G lambda squared equals 1 for each helical band separately. Now, disorder, once it is introduced, it significantly complicates the picture. So without disorder, you can think of these two helical bands as decoupled while only sharing the same superconducting gap. While when you add disorder, you actually mix the two bands by introducing interband scattering processes. Now, this disorder potential written here, it's actually just a simple scalar disorder, but it acquires this complicated form when you project it to basis of two helical bands. And then you need to introduce two scattering rates, two effective scattering rates, which for the two helical bands. Now, this Eilenberger equation in this form is a matrix equation, but we can simplify it significantly by introducing a few assumptions. So first of all, we will say that the phase gradient varies only along the x direction, and we will apply our Zeeman field along the y direction, which by symmetry are the conditions when the magnetoelectric effects are maximal. And then we parameterize our superconducting gap in space in this way: delta e to the EQX, where Q is a phase gradient which contains two contributions: Q naught, the intrinsic modulation of the helical phase, but also delta Q, which comes from an additional applied supercurrent. And then we take these ansatz for the solution, where tau z, tau plus, and tau minus are matrices in Ambu space. And we plug this into the Eilenberger equation, and instead of the matrix equation and differential equation, it is now a simple algebraic equation written here. So here, rho lambda contains both the phase gradient and the exchange field, and you see that the equation is actually quite simple if you remove the collision term on the right-hand side. So you will see that it's actually very simple to solve in the clean case, while complication comes when you introduce disorder. And then, so one needs to solve this Eilenberger equation and then plug the solution into the self-consistency condition. So we need to determine the order parameter delta self-consistently, and also using this delta later determine the current J. Now, in both expressions for this self-consistent delta and the current, we see that the contributions, the Green's functions from the two bands enter with different weights, so which is due to different densities of states. Moreover, there is a condition that the current at the Q naught, which is the modulation of the helical phase, needs to be zero, as it should be in the ground state. So now let us use the solution of the Eilenberger equation to quantify the diode effect in Rashba superconductors. So it's actually quite simple to solve the Eilenberger equation. So without disorder, we can simply invert, and this is the solution. Then the first step is to find delta of Q self-consistently, and as an example is written here. So for every phase gradient where delta gives a finite value, then using this self-consistent delta, we calculate the current J of Q plotted in red. Then we find the critical current in one direction as a maximum, in the other direction as a minimum, and calculate the diode coefficient, which is defined as the difference of the critical current divided by the sum. So this is the measure of the strength of the diode effect. So here on these plots, I show the results of this calculation done for several different fields. So at zero field, it's very simple, no diode effect and no helical superconductivity. So this is a well-known result. But then if we apply a field, then we see that the zero of the current is no longer in zero, but at some finite value Q naught. And in the upper right picture, Q naught is small. So here we are in a weak helical state, while in the lower two pictures, Q naught is large, proportional, almost equal to 2H. And here we are in the strong helical phase. Now, notice that in the lower two pictures, the self-consistency condition can have two solutions. So plotted in the in the full line and also the dashed line. One centered around Q naught and the other centered the minus Q naught. So the full one originates from the band with higher density of states, while the dashed one originates from the one with the lower densities of states. And we know that this one is more energetically stable and more, it minimizes the free energy. So this is the only contribution that we need for our calculation, while the other one can be safely neglected. And then we can look at the value of the diode coefficient. So here in the weak helical state, the value is minus 3.5%. So the minus sign means that JC minus is slightly larger than JC plus. But if we go to the other situation in the strong helical state, we see that the diode coefficient is actually positive. So there is a sign change of the diode coefficient where when you cross over from one type of helical state to the other. And here we plot for every point of the phase diagram, we plot the value of the critical current non-reciprocity. And then from here, it is clear that we have a region of negative diode coefficient, which is comes from the weakly helical state, and the region of a positive diode coefficient, which comes from the strongly helical state. You see that the magnitude of this eta reaches up to 40%, which is quite high. But notice here that increasing the magnetic field beyond beyond, let's say, 2 PC actually leads to the suppression of the diode effect. And this can be understood as follows. So the main driving force of the diode effect is actually the competition of the two helical bands, because they respond differently to the magnetic field. But once the magnetic field is very large, actually the only relevant band is the one with the higher densities of states, while the other one becomes irrelevant. And so you basically suppress band competition at sufficiently high fields, and then as a result, the diode effect vanishes. Now we can compare this result to the numerical study done by the Japanese group this year. And we see that qualitatively it describes the situation quite well. So in their case, there is also a crossover from one sign to the other of the diode effect. While here you notice that they can have yet another sign change, which is driven by their parameter T2, which comes from next nearest neighbor hopping. Well, this parameter is beyond our model, but the picture of the diode effects is quite rich, and the sign change can be achieved in many ways. But the main point is that that at low fields, at weak helical state, and at stronger fields, and strong helical state, there is a different sign of the diode effect, and this fact can be used to probe, for instance, helical superconductivity. Now, here in this slide, I plot the same phase diagram as before, but now for different values of spin-orbit coupling. And then, as you can see, actually increasing spin-orbit coupling actually leads to a suppression of the diode effect. So, for instance, here it's weaker, and here it's even weaker than before. And this can be also understood in terms of the competition of the two helical bands. So the density of the states of the two helical bands is given by this expression. And then if spin-orbit coupling is too large, density of states of one band is much larger than the other, which means that one band will dominate the physics of the superconductor, and therefore there is no band competition. In fact, if we set alpha velocity, Rashba velocity to be equal to the Rashba velocity, then we see that the density of states of the two bands are 0 and Q2 nu. So effectively only one band, and it is trivial to see from our Eilenberger equation that there should be no diode effect whatsoever in this situation, because one can simply gauge out the exchange field. Now, it is interesting also to look at how the diode coefficient depends on temperature at some fixed magnetic field. So this is what this plot shows. This is basically the same data as in the previous slide, but now plotted for some fixed magnetic fields. And what we can see here is actually that depending on the field, the dependence of the diode coefficient on temperature can be monotonously decreasing, but also it can have some non-monotonic behavior. And this non-monotonic behavior comes from the fact that the crossover of the helical superconductivity between weakly and strongly helical, this crossover field happens at different temperatures. Now, what we looked at so far is the full self-consistent solution of our Eilenberger equations, but actually we can do some more analytical results in the Ginzburg-Landau regime. So if we assume that our superconducting order parameter is small, that is, if we are close to the phase transition to the normal state, then the superconductor can be described by the Ginzburg-Landau free energy, where alpha Q and beta Q are the Ginzburg-Landau coefficients. Now note here that this is written in Q space. Usually it's written in real space, but for us it is more convenient this way. And then these coefficients alpha and beta can be constructed once you know the solution of your Eilenberger equation. So to construct alpha, you need to know the solution up to first order in delta, while to construct beta, you need the solution up to third order in delta. And this is very easily found from our Eilenberger equation. Then once we have this free energy, we first determine the delta by minimizing f with respect to delta. So delta squared is given by this expression. And then plugging this into the free energy, we get the optimized free energy given by this expression, and the current is then calculated from here. And this is the result. So here, the Ginzburg-Landau regime is shown in the lower plot. So here, the black curve is the upper critical field, and the dashed lower curve is where delta of t is equal to t. So in between these two curves is where delta or the parameter is smaller than t. So this is the region of the validity of the Ginzburg-Landau theory. And then, well, if we compare this to a full self-consistent solution, we see that it matches quite well. But we can do even more analytical results if we go to the regime close to TC and weak fields, which was addressed in previous phenomenological theories. So it's regime here. And then, so to do that, we may expand our Ginzburg-Landau coefficients up to first order in H, but we actually need to keep fourth order terms in Q in order to capture correctly the diode effect. And so our coefficients have this form, where these odd coefficients, alpha 1, alpha 3, and beta 1, they are all proportional to the Lifshitz invariant, so proportional to spin orbit coupling and the Zeeman field. And then if we plug all of this into our expression for the current and do the calculation, we see that the diode coefficient is given by this expression. So there are multiple contributions, but each one of them is proportional to spin orbit, coupling, Zeeman field, and this square root of temperature. But if you take them all together, they cancel out actually. So it turns out that there is no diode effect up to linear order close to TC, up to linear order in H. So, and this is in contrast with what previous studies claim. So for instance, these two, which actually find a diode effect proportional to this value here. So a finite value in this regime. And we think that this is due to the fact that they didn't consider all terms properly. So for instance, they missed the fourth order term in the free energy. And this is what leads to a false finite effect in this regime in their calculation. Now, this vanishing of the diode effect close to TC is actually in quite good agreement with our numerics. So both from the full self-consistent calculation and also from the Ginzburg-Landau calculation. Now, this was all that I talked about so far was for the clean case. But now let us add disorder to the system and examine the diode effect. So it is known that adding disorder to the Rashba superconductor, first of all, leads to the suppression of the upper critical field, the suppression of the divergence of the upper critical field at low temperatures. So for instance, here the black curve is for, in the absence of disorder, by adding disorder cuts off the divergence. But moreover, disorder actually increases the upper critical field at higher temperatures. So this is what you see, for instance, with this orange curve being much larger than the others. But more importantly is how disorder affects the nature of the helical state. So in the clean case, the black curve, we see that this crossover between weakly helical and strongly helical state happens. But as you increase disorder, these curves start to straighten out, and then you end up with one helical modulation of this type for all values of the field. So no crossovers anymore. So that means that the strongly helical phase is suppressed by the presence of disorder. This can be simply understood because disorder couples the two bands, and therefore in that way suppresses their competition. And based on this, we already expect that the diode effect will be suppressed in the disordered case. But our goal now is to see how exactly it is suppressed and at what value of disorder the suppression happens. So the first thing that you think of when you want to study diffusive systems is to start from the Usadel equation, which is the version of the quasi-classical equation for diffusive systems. So when disorder is very large. Now, very large disorder in this case means that it must be still smaller than the spin orbit energy alpha PF in order to preserve the structure of our equations. But even in that case, we see that the superconductor is described by this Usadel equation, which is formally similar to Abrikosov-Gorkov equation for magnetic impurities, where the effective depairing rate is given by this expression. And from here, we can clearly see that there is no diode effect within this equation. Now, one would need to extend the Usadel equation with higher order term in h tau and q tau in order to capture the diode effect, which would require deriving a new equation. So instead of this, what we use is the Atero raised his hand. Yes.
Yeah, just a quick question. I mean, don't you actually suppress superconductivity in this disordered case? Because, like you said, it's like magnetic impurities, and if you have strong magnetic impurities, you should suppress superconductivity.
At some point, yes. Well, you have this effective depairing rate. So based on the value of this effective depairing rate, you suppress superconductivity. So like in Abrikosov-Gorkov.
Yeah, or like Maki superconductivity.
Yes, yeah.
Yeah.
So yes, basically, yeah, we use the full Eilenberger equation to describe the diode effect in the Ginzburg-Landau regime. So here are the results. So the different panels here corresponds to different values of disorder. So we do exactly the same as in the clean case for the Ginzburg-Landau regime. So these stripes here are the regions of validity of the Ginzburg-Landau theory. And what we can clearly see is that we start from one regime in the clean case, and as we increase disorder, we see that the behavior qualitatively changes. So the diode effect goes to positive to negative, and this is a consequence of as we shown before that negative diode coefficient is actually associated with weakly helical phase. This is what we have in the diffusive limit actually. So due to the change in the nature of the helical phase, we have a change of sign of the diode coefficient as we increase disorder. Now, here we do it only in the Ginzburg-Landau theory. Now, our theory would, in principle, allow us also to calculate, to fill out the rest of the phase diagram, but this is very technically challenging, so we left this problem to some later study. But even here, even only within Ginzburg-Landau theory, we are able to verify that the effect exists up to strong disorder, and that it is qualitatively different from what is seen in the clean case. Now, in these plots here, we show what happens to the diode coefficients in a broader disorder range. So first we plot the upper critical field at some fixed temperatures as a function of disorder, and we plot the corresponding helical modulation. And then we work in the vicinity of this HC2. So we go along the upper critical field just below it, where superconductivity is weak, along these curves, and calculate the diode coefficient at each point. So this is what is shown in this picture. And what you can see, so for instance, if you focus on the black curve, which is at low temperatures, in the clean case, there is no diode effect at 0.2 TC. But as you increase disorder, there is a crossover to this weakly helical state, and up until, let's say, 10, where 1 over TC is 10. And then further increasing disorder actually suppresses the diode effect, so it goes to 0 as disorder is further increased. So this demonstrates that the diode effect actually can have a substantial value in a very large, even for very large disorder. Now, so far, I've talked about theoretical aspects. So I've shown that the diode effect is quite strong in the clean case, but also substantial diode effect exists also in the diode case, the disordered case. But now let me talk about more on the practical side, how one should measure this. So the device that we proposed in our paper looks like this. So we have a superconductor, which is sandwiched between a heavy metal insulator and a ferromagnetic insulator. So the job of these layers of the ferromagnetic insulator is to introduce an interfacial exchange field, so the Zeeman field within the superconductor, and the heavy metal insulator is to introduce the spin orbit coupling. And then basically one has all the necessary ingredients to achieve the diode effect. And this device should work even without applying the external fields because of the magnetization of the ferromagnetic insulators. But this kind of device was actually fabricated by Jagadesh Modera from MIT, our collaborator. So a similar device where we have platinum, vanadium, and europium sulfide, where platinum provides spin orbit coupling and europium sulfide is the ferromagnetic insulator. And indeed, they measure a quite large diode effect, which is actually larger than any theoretical predictions that we have, so up to 60%. But it turns out that this effect is not due to spin orbit coupling, because you can remove the platinum layer and still observe the diode effect. And moreover, if they put oxide layer between a superconductor and a ferromagnetic insulator, and this way prevent the contact and the interfacial exchange field, they also measured, even in this situation, the diode effect. So that means that this diode effect that was measured has nothing to do neither with spin orbit coupling nor the exchange field. And what is the most plausible explanation actually is that the stray fields of the ferromagnet actually penetrate the superconductor, creating a screening current, and then the critical current along the screening current and opposite to it is different, leading to the diode effect. So in order to prove the diode effect in structures with spin-orbit coupling, it would be tricky with ferromagnets. So probably the best course of action is actually to apply a field with some superconductor with strong spin-orbit coupling. Another possibility is to combine van der Waals materials in heterostructures. So for instance, nickel dibromide is a 2D ferromagnet, and then with one of the many 2D superconducting materials. And this way, one could engineer a heterostructure which would show a diode effect. So to conclude, we use the quasi-classical formalism to describe the diode effect in Rashba superconductors, and it provides a very straightforward framework to do this. We see a very strong diode effect up to 40% of efficiency in the clean limit. And we see that the nature of the helical state, so either strongly or weakly helical, determines both the magnitude and the sign of the diode effect. And moreover, it persists at a strong disorder. Now, before I wrap up, I would like to point your attention to our previous work that Ilić mentioned. So this is yet another type of superconducting diode, but this is a diode for quasi-particle currents. So there is a tunneling barrier, and the diode effect is achieved by the electron hole symmetry breaking due to a combination of spin splitting of a superconductor and the spin-dependent tunneling barrier, which is also present in the system. And this situation is covered in these two publications. So this is all. Thank you for your attention.
Thank you, Stefan, for the nice presentation. Now it's time for questions. So anybody needs to wants to ask a question? Okay, we have Christoph Strunk. I should probably unmute. Let me see.
Okay, so I was
okay, you can do better.
Simply, but if I get the word, I also have a question. Namely, whether the sign of the diode effect can also change in the diffusive regime, or whether it has only one sign there.
Yes. Well, I would say you're saying that if we go deeper in the phase diagram, for instance, here, if we would do this calculation, you're asking if we would see
Yes.
something else. My feeling is not. Because in the diffusive regime, you don't have such complex crossovers between strongly helical and weakly helical phases. So in the diffusive regime, you have only one type of helical state. So, but this is something that we can check once we do the full calculation, which we might do in the future. So short answer, I expect that no, that it should be like one sign only.
Thank you very much.
Now I think it's time for Chun-Li Huang. And yes.
Yeah, thank you, Stefan, for the wonderful talk. I'm not sure if you're aware, like recently in this twisted tri-layer graphene, people have managed to see the superconducting diode effect without any magnetic field. So apparently the system itself breaks, generates some sort of exchange condensation so that it becomes an orbital magnet.
So there are no ferromagnets in the system. So the time reversal symmetry breaking comes from graphene only.
Yeah, so the system itself, Coulomb is strong enough, bandwidth is small, and they break time reversal. Now, so I was wondering, in this Rashba system, you can, instead of having an exchange Zeeman field H that you put in by hand, you could also generate spontaneous spin polarization self-consistently, right? And how do you expect that to change this picture?
So the main ingredients that you have, as I said in the beginning, if you have both time reversal and inversion symmetry breaking, if you have these two ingredients, this
is it my side or I can't hear you?
No, we lost your voice, Stefan. Can you try to connect your microphone?
yeah, is it better now?
Okay, now it works.
Yeah, you're back. Yeah, good.
Okay, so the main point is, in order to achieve the diode effect, you need to break two symmetries, inversion and time reversal. If these two symmetries are broken, you have all the symmetry conditions needed. So, and what you describe, I think, breaks the necessary symmetries. So I would say that I would expect the diode effect in that kind of system. Now, how it should behave, how it will be different compared to what I've shown here, I'm not sure.
Okay, yeah. I'm just wondering, because you have to solve one self-consistent equation for the superconducting gap, but you could also solve for the exchange gap.
Yes.
Right. Self-consistently, and that way you don't have to put in the external field by hand. Yeah. So,
and this is something that can be done also within this helical basis. So it will be the same formalism, just with another additional ingredient, right?
I think so. If you put in strong enough Coulomb exchange, you know, you should get magnetism out, because the spin would like to cant out of the plane, right? Yeah, and I don't know how that will influence the superconductivity. But in principle, it is that, the instability, the magnetic instability. Yeah. Thank you.
Thanks.
May I comment on this?
Yeah.
Yes, please.
In the graphene case, I think the presence of valleys is very important. So the symmetry breaking is actually there is this valley valley dependent chemical potential that actually is the relevant symmetry breaking parameter. So and this valley doesn't exist here. So that's kind of the difference.
Yeah, but valley sort of is time reversal partner. So if you polarize valley, then you probably kill
you break the time reversal.
So probably kind of so probably it's spin polarized, not valley polarized. I think that would be the answer. Yeah.
Yeah. Okay. It's true.
Okay, thank you. And now it's time for Alex Matos.
Okay, thank you, Stefan, for this nice talk. I have a question regarding this result that the diode effect will vanish at linear order in Rashba. So how general is this? Is this just because you are close to the transition, or is it just because you are in this regime that very large alpha or very large spin orbit with respect to the Siemens?
So you're right that this, so in order to get the vanishing diode effect, I am assuming very weak Zeeman field and close to TC. So this is true only in this region of the phase diagram, only here. And if we, for instance, included more ingredients in the theory, so for instance, if we allowed for interband pairing, which is neglected in this theory, so this might bring some additional ingredients, which I'm not sure how it would influence the diode effect. So this is only true if Rashba spin orbit is very large, so that we can neglect interband pairing.
Okay, and so in this approximation, then, what will be the lowest order in a spin orbit that is on zero?
It would be h squared. So we would need to go to h squared order, but actually working with the full Ginzburg-Landau theory with the arbitrary order h and q is actually easier than doing all this expansion to higher orders. So I think this kind of theory, which is presented here, would be the way to go, a simpler way to go.
But it's still, so still you will have something that is linear in Rashba, but higher order in field, is what you said? Or do you need to go to higher order in Rashba too?
I think linear in Rashba is sufficient because the only way that Rashba spin orbit enters in these equations is up to linear order through the different densities of states. So everything is linear in Rashba in that sense.
Thanks. Thank you very much.
Thanks.
Okay, so if there are no more questions, we can thank the speaker again and thank you for your presence here.